Okay, so quick review of where we are. If you can do this, then you should be in really good shape based on where we are currently on this section. Okay, so I'm going to copy this problem down where you can actually see it. So it gave you this function, said 2x cubed minus 9x squared plus 12x minus 1. And it says, and it gives you this, and we're only considering this function on the interval from -1 to 2. Right? So from -1 to 2 is the only place this is defined. Now normally you'd look at this and say, oh, polynomial, a cubic function. What do cubic functions kind of look like? Kind of like this, right? And if it's +2, it heads up high, comes back down, probably has a wiggle, and then goes low to the left. But I don't know if it looks like that on the interval from -1 to 2. So normally if I saw a function like this, what would you say the max was?
Infinity.
Would you?
There's not one.
You'd say there's not one, right? You'd say the max does not exist because there is no y value bigger than all the others. And what would you say about the min? There isn't one. But this has an interval. And we have learned through the extreme value theorem that if you have a continuous function, right? This is the EVT. If you have a continuous function, which I do, it's a polynomial, they're always continuous, on a closed interval, then there's no way it can go up forever or down forever. So there will be a max and there will be a min. Even if it's a horizontal line. If it's a horizontal line, the maximum y value would be whatever that y value is that exists everywhere. And the max and the min would actually be the same. But if you have a continuous function on a closed interval, you will have a max and a min, that's guaranteed. That's the extreme value theorem. And I know I'm throwing these theorems at you and you're like, so what? But these are all going to come into play and we're going to be using these throughout the year. All right, so first question is, are you guaranteed to have a max or min in the interval?
Yes.
Absolutely. Why?
Because it's closed.
All you have to say is EVT. The EVT guarantees this. Now, if somebody said, what does the EVT guarantee? Then say, oh, it guarantees a max or min on a closed interval if the function is continuous. But that's all you have to say. Now, why? Because that's the limits of the EVT. What theorem? We already said that as well. Okay, number 2, where can a max occur on a function? What do we say in the lessons we've been watching? A max can occur either in one of 2 places. Critical points or endpoints of a closed region. Okay? Now we're going to learn some things after this about critical numbers, how to actually test for relative maxes and relative mins using these derivative tests that we're going to learn. But as of right now, critical numbers, maxes or mins for that matter, are critical numbers or endpoints. All right, next question. How do you find critical numbers?
You said the derivative equal to 0.
Yeah, you set the derivative equal to 0, the solution to the derivative when you set it equal to 0. And why is that? Because the derivative is the...
Tangent.
No, it's the what? Slope of the line that's tangent. And if the derivative is slope, and I set it equal to 0, I'm finding where the slopes are 0. And if you think about it, when the slopes are 0, what could occur there? A little bump up, which is where a max might occur. Or maybe where a min might occur. Now, it doesn't have to do that. It might go up like this and flatten out for an instant and then keep climbing. So sometimes critical numbers don't, and by the way, critical numbers are not just where slopes are 0, but they're also where slopes are D and E are undefined. Because sometimes you'll get a thing like this, it'll curve up like this, and then curve the other way, and it makes a what? A cusp, still a max up there, or maybe a relative max. Now, I don't know what happens in other areas. It might go up higher somewhere else. But that's why we call them, well, that's not why we call them critical numbers, but we call critical numbers those possible places where the relative maxes might occur or relative mins might occur. And then I got to go check and see which one's the highest. So what I'm going to do is not only just check those critical numbers, all right, but also check the endpoints when it comes to a max or min. But this just says, how do you find them? Yes, take the derivative, set it equal to 0, or DNE. And on this problem, you're going to see the derivative is not going to give you a DNE, because you're not going to get anything in the denominator or any place where it's undefined. Next question. Where can relative maxes and mins be found? We've already said that at the critical numbers. Can a relative max or min be found at an endpoint? It's important to know this. A max or a min can, but a relative max or min can't, because a relative max or min You have to be able to look on both sides, right? It has to be literally the max relative to the points on either side. And if it ends, there are no points on that side. It's really important that you get that down, okay? And we're going to get to relative maxes and mins very soon, but not today. And then it says, are all critical numbers going to be places where relative max and mins occur?
No.
No, for the reasons we just said, right? Because it might go vertical. That's a critical number. That x coordinate is a critical number where it goes vertical, but that's not a max or min. Or it might come up and flatten out, but then keep going. We call this a layout, a horizontal layout, or we could call that. All right, so anyway, we've answered all these questions. The last thing is find the max of this function on the given interval. So to find the max, I need to check the critical numbers and the endpoints and see which one has the highest y value, right? So I'm going to take the derivative, and by the way, AP wants, they're going to give you points for showing your intelligence. I know a lot of you just do this kind of stuff. 6x squared minus 18x plus 12, divide a 6 out. Don't do this, by the way. Factor, and okay, 1 and 2, and they're both in that interval. All right, I'm good. So 1 and 2 are my critical numbers. But guess what you didn't tell AP that you knew?
Equals 0.
Yeah, first of all, you didn't even say what that was. You need to label stuff. I'm taking the derivative. Oh, and the derivative is equal to 0. Now you would get points for this, but they are literally assigning a point to you for showing that the derivative is equal to 0. Heck, if you had a brain freeze and forgot how to take a derivative and just wrote down the derivative is equal to 0, you're going to get a point out of that, even if you don't take the derivative. They need to see this kind of information, and so do I when I grade these, okay? And then when I go and actually solve it and try to do your work nicely so they see stuff, I can see that those values work. And you can factor the 6 out. That's probably what I would do, but to show everything, all right? But the factor, if there's no x with it, it doesn't count towards a root. We know that, right? That's a mistake I see every year. People go, oh, my roots are 1, 2, and 6. No, there's no x there. It doesn't contribute to a root, all right? Now, also, mistakes people made, and I probably should have given you a little bit better problem here, but both of these numbers ended up being that interval. It's totally likely to get numbers like 1 and 3. Well, would 3 be a critical number here if it was 1 and 3? No, because it's not even in the interval we're talking about. Now, if I'd opened the interval up for you, then yeah, it might have been there, but you got to look at these and make sure you check the interval. So this means these are my what? My critical numbers. And by the way, you're going to be doing things in a few days called, you're going to be finding inflection points. And inflection points are places where the graph changes what we call concavity, where it goes from like concave up to concave down. And those have value too, especially when it comes to position and velocity, acceleration, and things like that. But critical numbers are x values. Inflection points are points. So if I ask you for a critical number, make sure you don't give me a point. You're giving me literally the x value. And then when we get to inflection, I'll hammer this in over and over, and when we get to inflection points, make sure you're actually giving me a point. So those are my critical numbers. And these are basically, again, places where the graph has a slope of 0, or maybe a slope that's undefined. And these are places where the graph could possibly have a max or min on that interval. But where else?
At the interval, so at -1.
At -1 and 2, okay? So the way I do this, don't do this. Okay, if I plug a 1 in and plug a 1 in there, it gives me 4. That means nothing to the AP reader. 1 arrow 4. There's math that suggests what you just did there. What did I just do? What is that?
F of 1.
F of 1, say that. F of 1 is 4. Now if you're like, why didn't you plug in the derivative? I don't want to know the slope there. What's going to happen if I plug a 1 in there, by the way?
You'll get...
I'm going to get 0 because it was a solution to that, right? I already know the slope is 0. I don't care. I want to know what's the y value there because, again, I'm looking for the max. I want to know what's the biggest y value. So I'm going to check these critical numbers here and here. And I plug a 2 in and I get what? 16 minus 36 is -20 plus 24 is 4 minus 1 is 3, I think. Hopefully I didn't make an error. And then I'm going to check the endpoints. And since I've already checked 2, that's both a critical number and an endpoint, right? I don't need to recheck that again. I'm going to check the -1 f of -1, that gives me -2, minus 9 is -11, minus 12 is -23, -24. So what's the max?
4.
4, not the point, because remember, maxes aren't points, maxes are y values. Now, sometimes in an AP test, they'll say, hey, at what x value does the max occur? Well, don't say 4 then. What x value did the max occur? At 1. But if they say the max, you say the max is 4. And if they said the min, although I didn't ask, the min would be -24. And that's assuming I did my calculations right. I think I did, but I'm just doing them off the top of my head. Are y'all with me? And that's what you should know from the other video. So if you're looking at this and you can answer all these questions, you're like, oh, I'm in good shape on this. Great. If you're not, go back and make sure you know these definitions. If you try to cram all this in on test day, you're going to get smoked on this test. You really are. I've broken this test up into 2 sections this year, so we're going to be able to isolate them a little bit better, and you won't have to have so much running around in your brain, and we're going to do just definitions on this test, as opposed to definitions and curve sketching, but it's still important, and I did that mainly, well, originally I was trying to sneak it in this 9 weeks, but then it just didn't, I couldn't sneak it enough, and give you the 9 weeks test. Are y'all with me on this? Okay, so here's what's new, and we're going to take a little bit of a break. This really syncs a little bit better with what we're going to do tomorrow, but I've always done it this order, and it kind of makes sense to me. So I'm on page 113, and we're talking about the mean value theorem, one of the more critical formulas and the most questioned formulas on your AP test. And if you get this down, it's like taking candy from a baby most of the time, because it's really hard to create new, unique mean value theorem questions. It's just really hard. You rarely see unique ones. It's usually just regurgitating what you already know about the mean value theorem. And the mean value theorem, as I'm going to explain it, is really obvious. Like when you're going to look at it, you're going to go, duh. But they're clever in the way they ask it, because they sneak little things on you. And if you don't know the rules for mean value theorem, it can get you into trouble. Okay, or the conditions. So let's check it out. The mean value theorem says this. Okay, and it starts very similar to the extreme value theorem. If f is continuous on a closed interval, and that was the 2 conditions for the EDT, right? But they're going to add one more. And differentiable on the open interval. Now what does that mean? Continuous on the closed means it starts at A with a point, starts at the x-coordinate of A somewhere with a point, ends at the x-coordinate of B with some point, and it never breaks, right? No holes, no vertical asymptotes, whatever. But with just that, I could have cusps in there, couldn't I? Yeah. Or I could have going verticals in there. But if I say, hey, wait, it's also differentiable on the interval, what does that mean? Then there aren't any custom corners and junk like that. So if that happens, now I don't have to make that closed, because you can't take a derivative at an endpoint anyway, can you? No. If you're wondering why, remember derivatives always go back to what? A limit, and a limit has to come from both sides, and it does. So anyway, so it's continuous on the closed, differentiable on the open. Those are the conditions. If that's true, then you are guaranteed. Okay, this is a little example. Here's a little section from A to B, and you can ignore this other part right here. All right, there's A and B. There's a point there, and you can see the curve in there. So from A to B, this curve, because it was continuous with no breaks, differentiable, right, with no cusp corners and all that kind of stuff, then you are guaranteed somewhere on this graph to have a x value where the slope of the curve at that x value matches the slope from beginning to end. Guaranteed. Now I know you may be thinking right now, that is like not a big deal. Why are we even talking about this? You'll see later. So what did we call the slope from one point to another? I actually gave you a test question on it. Towards the end, I gave you a little chart. Average rate of change. And average rate of change is just slope, right? And I asked you on that graph, I said, and most of you got it right, I said, and a couple of you missed it because you probably didn't check every slope and you were just eyeballing it. But there was a question that said, what is the average rate of change? And I think it ended up being like 3/4 or -3/4. And almost everybody in all my classes got it. And the other one said, where's the average rate of change the biggest? And most of you said C to D, although there were a couple of you said D to E, because that would That was kind of close, I guess. But anyway, average rate of change is just slope from there to there. So I go y minus y over x minus x. That's the slope. Well, that's that. All right? So the average rate of change says, the mean value theorem says, that at some value of c, the slope at that c, so that's the derivative of the function, the slope at this c value is going to be the same as the average rate of change from a to b, which is the slope from beginning to end. That's it. And I'll show you some examples. The derivative of the function at that value has to exist somewhere, okay? And it will match the average rate of change, which is the y minus y over x minus x from beginning to end. That's it. And it might happen a bunch of times. And the math will let you know where that c is. So check it out. But that's all this says. So first question says, verify the mean value theorem. Well, if I were you and anybody ever tells you to verify the mean value theorem, then write it down to start with. Bam! Because you get a point for that on an AP test, on a problem like this. And if you don't write it down and you end up showing the derivative and showing the fact, you're going to still get credit, but you get credit for that statement or for this statement. Now, the right statement says, hey, what's the slope from beginning to end? Well, you have the x values at the beginning and the end, right? Right? There's the x value at the beginning, -1. There's the x value at the end, 2. So to find the points, I just plug -1 into the function to find the y. Well, that's what that is. And then I plug 2 into the function to find the y. That's what that is. And then I just go 2 minus -1. So y minus y over x minus x. So if I plug -1 into that, I end up getting 14. So I write that down. If I plug 2 into that, I end up getting 17. I write that down. And then I just go 2 minus the -1. So this is me finding slope. But if I were you, I would write this right here. Because that's really showing that you know to go y at the end minus y at the beginning over x at the end minus x at the beginning. That's the slope part. That's average rate of change. So that's the slope from beginning to end. And what is the slope from beginning to end going to match, guaranteed? The instantaneous rate of change, absolutely, which is the slope at some x value. Now, a lot of people get a little sloppy, including me, and they just leave the x in there. If you want to do that, that's fine. At the very end, you'll have x equals 1/2. Right? If I take the derivative of this and get 8x minus 3, right, the derivative of f is 8x minus 3, the derivative at some x value, they call it a c value, is going to match the average rate of change. It's just a matter of finding where the x is. So you do the math here and you end up getting 1, right, 3 over 3. Add a 3 to it, you get 4. Divide by 8, you get 1/2. So what does that stand for? No, what is that right there you just found?
Slope.
Is it? Think about it. What did you just find? The x value. You just found the c, or the x value, where what occurred?
The same slope.
Where the slopes matched. Does that make sense? You just found the x value. Now, a lot of times they'll say, what is the slope? Well, now that I have the x value where it occurred, what can I do with that x value?
Plug it in.
If I wanted the slope, I can plug it in, right? So if I wanted to take 1/2 and go back and plug it into that derivative, I could, and I'll get a slope of 1 there, right? 8 times 1/2 minus 3. But this is, it says, verify the mean value theorem. So I verified it because I said, all right, do I have a function that's continuous on the closed? Yes, all polynomials are continuous. Do I have a function that's differentiable on the open interval -1 to 2? Yes, because polynomials are always what? Differentiable, because they don't have cusps on them. They don't go vertical. By the way, where do you see cusps anyway? Maybe piecewise functions or fractional exponents. That's when you see weird stuff like this going, cusp. Remember the x to the 2/3 graph? Remember the x to the 1/3 graph? That's where it does that jump. Polynomials don't act that way. Polynomials are always continuous and differentiable. So those two check marks work. The only other thing I need to check is, can I find that x value where the slopes match? Just did. So I have checked all the boxes of the mean value theorem. So yes, can I verify this? Absolutely. And I guess I could write out at x equals 1/2, And Jack said this great a second ago, the instantaneous rate of change. Remember, a derivative is the slope at a value. The instantaneous slope equals the average rate of change from beginning to end. That's what average rate of change is, slope from beginning to end. So the slope at that spot at C is the same as the slope from beginning to end. And you just verified the mean value theorem. All right, let's look at another theorem that's very similar. And by the way, I even commented on this. Rolls must have been desperate to get his name out there, because Rolls took like the most knowledge of the mean value theorem and wrote his name on it. You don't even know who came up with the mean value theorem, but Rolls is like, oh hey, I got some brilliant logic here, and you'll see how bland it is. But here's your mean value theorem, right? The derivative at some x value is going to be the same thing as f of b minus f of a over b minus a. That's the MVT, right? Got with me? Now here's Rolls. Hey, I got something to offer. What if your points are at the same y, that have the same y value at the beginning and end? Right? So if I plug an a in on my closed interval, I plug it into the function and I get a y value, and then I plug the b in and I get the same y value. So basically, if my f and my a and my f and my b are the same, then here's my theorem. There's guaranteed to be a derivative that's equal to 0. Well, duh, because if the y values are the same, what happens to your slope? It becomes 0. So I don't know why this is worthy of putting your name on it and going, who Rolle's theorem? Glory to Rolle. But right here, this to me is the mean value theorem. And on your AP test, if you run into a situation like this, you're welcome to quote Rolle's theorem. But Rolle's theorem is basically the same thing as the mean value theorem. Rolle's just says, he has the extra condition and says, hey, if the y values are equal, well, of course, if the y values are equal, when you subtract them, you get 0. And if you get 0 there, the whole fraction's 0, right? So he's just taking the mean value theorem, putting his names on it, trying to be impressive. But the bottom line is, if your average rate of change is 0, which means the slope from beginning to end is 0, well, of course you're going to hit a 0 somewhere, right? Maybe in a bunch of spots. Y'all seeing that? But what that does for you, it's just one more checkpoint. So if anybody says, hey, what are the conditions of Rolle's theorem? We'll just think mean value. It's got to be what? Continuous on the closed interval, differentiable on the open interval, but one other condition for Rolle's.
F and A has to equal to B.
So the y values at the beginning and the end are equal. And if those three things, continuous on the closed, differentiable on the open, and that equals that, well then you can just say, oh, it's mean value theorem, but all of this goes away and just becomes a 0. You all with me? But it's the same thing as the mean value theorem. I mean, if anybody just said, hey, is there a slope of 0 here? Is there guaranteed to be a slope of 0 on this function on that closed interval? You could go, yeah, I can plug it all in here, and the slope from beginning to end is 0, and I could find those values, just like I would on the mean value theorem. Because the only difference is mean value theorem says slope matches that. This says, since that's 0, slope has to be 0 somewhere. To me, it's the exact same thing. I don't think he's being a genius here. But how could these questions be asked? Oh, by the way, you'll notice right here, on this interval, this closed interval, there is no slope of 0. Is there?
No, because it's not differential.
It's not what? It's not differential. It didn't meet the conditions. AP likes to ask questions like that. They give you a function, they say, hey, why does this violate Rolle's theorem? And you'll go, because they'll say, hey, it's continuous on the closed interval, and then they'll say something like, the average rate of change is 0. Why doesn't Rolle's theorem hold here? And Rolle's theorem does hold here, right? Because it also would have to be differentiable on the open interval, and it's not differentiable because there's either a corner or a cusp there, depending on how steep that gets. What about this one? It's not even continuous, right? So if any one of those rules breaks, Rolle's theorem or mean value theorem gets tossed out, right? So, but it will hold if the conditions are met, all right? So right here, example 1, verify Rolle's theorem on that interval. Well, what do you have to verify for Rolle's?
Continuous.
It's continuous on the closed. And we know that that's true because it's a polynomial. And it's
Differentiable.
differentiable on the open interval. Don't have to worry about endpoints. But I know that's true because it's a polynomial.
Yeah.
And then what else?
It's all even exponents, so
The
it's
y values at the beginning and the end are
even.
the same, right? So the y at the beginning and the y at the end are the same. So since they're the same, and I checked them, I would have to plug it in to get that 8. But because, and yes, it is an even function. Is that what you're saying?
Yeah.
Yeah, so even functions means opposite values of x give you same values of y. And he looked up here and went, oh, that's going to happen. That saves you a little trouble for plugging them in, certainly. But because I verified that, I've gotten points for, this is like maybe a 3-point problem on an AP test. Verified, check, check, check. I know that that's going to be true. So that would be the verification. And then it says find the values of x, which they could call c also, right? It's some x value. On that interval where the derivative is 0. Well, I don't really need mean value theorem anymore because I've already shown that the average rate of change would have been 0 because the y's are 0. So I can jump straight to, well, the derivative somewhere is going to be 0. And I need to have that stated there or here. So what do? Just like I did in the mean value theorem, I take the derivative, 4x cubed minus 4x, set it equal to 0, and I am showing that the derivative is 0 there. That's the mean value theorem. I'm sorry, that's Rolle's theorem. The mean value theorem, what would it be over here on the right?
The whatever the slope of
The slope from beginning to end, the average rate of change. Okay? But in this case, I've already verified that that average rate of change will be 0 because the y's are 0. Bam. And then I factor out 4x, factor the x squared minus 1, and 0, negative 1, and 1 are the 3 points on this interval. And are all 3 of those in there?
Yeah.
Yes, so this one actually had 3 places where the graph hit 0 on this function. Which makes sense because it's an x to the 4th, right? X to the 4th come down, and back up, typically. Well, there were 3 places where there were, these are technically critical numbers as well because it's where it's equal to 0, but 3 places where you know you hit 0. Not too bad. Verify Rolle's theorem for this one. Now what do I have? It's not a polynomial, it is a rational function. And rational functions are like polynomials, and that they're continuous and differentiable everywhere except maybe where? Holes and vertical asymptotes. Those are the only 2 places. So when I look up this, I go, all right, verify Rolle's theorem on that interval. Well, let's see. I know that rational functions are continuous everywhere except possibly holes or VAs. And those always occur where? I always get a signal that there's a hole or a VA from what? From the denominator, right? And this is why I said go back and review your rational functions notes, and I put those in there. If you skipped over that, you really need to go back and review VAs, holes, things like that, because they will come into play here. So if I took this denominator and said, where does that denominator equal to 0? I would get x equals 15/8, right? Which is about what? Well, it's a little bit less than 2. Is that in that interval?
Yes. No.
No. 3 to 5 does not include less than 2, does it? So do I have to worry about that?
No.
No. So this, to me, this is the only place where it would not be continuous, therefore not differentiable. So everywhere else it's going to be fine, just like a polynomial. Now, if that interval had been negative 3 to 5, then yeah, that would have been included, right? But it's not, so I don't have to worry about that a bit. So verify Rolle's theorem. Is it continuous on 3 to 5? Yes. Because the only place it wouldn't have been is not in the interval. And if you're like, well, how'd you pick that interval? It's just randomly given to you. Is it differentiable on that? Yes. How do I know that? Because the only place it's not differentiable on rational functions is, again, holes and VAs. And there weren't any holes and VAs in that interval that was given. So you're good on those. So what's the last thing to check for Rolle's? Are the y values the same at the beginning and the end? Now, if I was saying verify the mean value theorem, you wouldn't even have to check that. But to verify Rolle's theorem, check the y value. So plug a 3 in, 9 over 24 minus 15 is 9 over 9 is 1. Plug a 5 in there, 25 over 40 minus 15 is 25 over 25, also 1. So since the y values are equal, the continuous and differentiability checks were met, you checked it all off and verified. And you gotta say this stuff. Don't just go, yes, it's verified. I'm gonna say why. AP always says why, or explain your results, or justify your answer. That's a big go-to, justify your answer. I just justified it. Okay? Now, again, I made a comment about the 15/8. I don't have to worry about it on this particular problem. Now, what if the interval was -1 to 5? Then is Rolle's verified?
No.
No. Now, could there still be a slope of 0?
Yes.
That's possible, but it's not guaranteed. And remember, what we're talking about here, verify means basically guarantee, show me the guarantee that it's gonna work. And I've met the 3 conditions, I know it's guaranteed. Last question, find the values where the derivative is 0. Well, take the derivative of this. How do you take a derivative of that function? Low D high minus high D low. I had a lot of people going high D low minus low D high on the test. I don't know if you caught that, but we gotta get better, right? So what do? I take the derivative low D high minus high D low over low squared, and I write derivative equals 0 somewhere on this to get that point, right? Sometimes it feels like when you're taking this test, you're just kind of scrounging, just point grubbing. But you do, and remember, you don't have to make an A on the AP test to get a 5. You make a low D, 62% or something like that gives you a 5 on it. Okay, you can fail the crap out of it and still pass it and get college credit, depending on where you go to school. So we don't want to do that. We all want to get really good scores, and listen, there's some really strong people in this group of calculus people. I mean, there really are. There's probably 7 or 8 of you that should be in BC class. I mean, you really should. But you're not, which I will happily take your 5. But we stand to have the best averages ever. I mean, if we didn't have this alternating crap where you were forced to do stuff from home, I really think we'd have some. We may break the record on number 5s in an AP class. I really feel, I'm not just blowing sunshine. I really think that's possible. So now, here's the difference now. You got to solve it. So how do I figure out where the derivative is 0? The derivative is 0 is all about what part of this derivative?
The numerator.
The numerator. Because think, even when I simplify, which you're going to have to do, by the way, we haven't done a lot of that. I distribute it, multiply, add like terms, and I get to here. A fraction is equal to 0 when its numerator is 0. So set it equal to 0 and solve it. Okay? Now, where else do I need to check? Well, derivative is 0, that's all I'm checking actually in this one. If I was checking critical numbers, I would set the bottom part equal to 0. But that's going to give me 15/8, which is not even in this interval. So I still wouldn't have counted it, even if it did ask me what the critical numbers were. So right there. So at 3 3/4, or 15/4, there's a guarantee. Oh, by the way, 0 was an answer too, but 0 is not in that interval. Right, when I set it equal to 0 after factoring. So 15/4, I'm guaranteed to have a slope of 0 there. And I knew that. I knew there would be at least 1, because the conditions were met. Right?
Right.
Okay, here's an AP question on mean value theorem. How many I got? Is that it? Yeah, that's gonna be it. How much time we got?
You got it.
7 minutes? Okay. So it says the graph of y equals f of x, which they didn't even tell me what it was, is continuous on the closed interval. I gotta tell you, if you're doing AP questions and they start throwing stuff at you, make a picture, because your brain is going to be guided towards information visually a lot better than just mentally. So check this out. I'm going to say, all right, on the interval from -3 to 7, I've got a function that's continuous, and it's differentiable there. So that tells me from somewhere over here to somewhere over here what? It's nice and smooth with no breaks and no corners, no cusp, no going vertical, no nothing. So it's probably a polynomial looking thing, all right? Then it says, it begins and ends with -3, 4. So I'm somewhere up here at 4, and 7, 2. Okay? It says, based on this information, there is a C. What are they talking about here? There is a
Point.
Is it?
Oh, X value.
There is an X value in between here and here, so there's some C somewhere in there, right? Such that what? Now, based on this, is there a guarantee that the value of F will hit 0?
No.
Now, it could, right? It could come down there and hit 0 a bunch. And if it did, by the way, it would have to hit twice or bounce, right? But there's no guarantee on that, right? It says value of c, not derivative. And even if it said did say derivative. What about this derivative? Is there a guarantee?
No.
When is that guaranteed?
Rules.
In Rolle's theorem, but with Rolle's theorem, what would you have to have?
The y values and two starting.
The y values are the same. Now, if that said 7, 4, do you see how they sneak that on you? They go, oh wait, the y values at the beginning and the end are the same, then that would be guaranteed. But the y values are not. Now, does that mean that this doesn't have a slope of 0?
No.
No, it can totally have a slope of 0. You can have a slope of 0 a bunch of times, but it's not guaranteed, and that's what this is asking about. So no. Now, the derivative equals 1/5.
No.
Now, it could totally be 1/5, right? It could go up like this and go, oh, there's a 1/5, but it's not guaranteed. What about negative 1/5?
Yes.
Why?
Well, because that's the slope.
Because the slope from beginning to end, which is the average rate of change,
Yeah.
if I go f of 7 minus f of negative 3 over 7 minus a negative 3, and by the way, I already know what f of 7 is, right? It's 2, so 2 minus the 4 over 7 minus the negative 3, and what does that give me? Negative 2 over 10. So this is saying that the average rate of change is negative 1/5. And what does mean value theorem say? The derivative somewhere is going to equal the slope from beginning to end. I know this is true. Do you see how this is the mean value theorem?
Yes.
All right, and they didn't even tell you it was mean value theorem, but that's all they're checking.
How does that work, like, in the graph? Because the graph is gonna have to, like, curve some point, and some point it's gonna have to.
No, it could have been a line. If it's that, then negative 1, then actually there's an infinite number of c's. If it was a line, right? If it did this, then yeah, somewhere. If it did this, then it hit there, there, and there. You would end up finding 3 c's if it was something like that. But no matter what happens, you're gonna have that. Unless it's not differentiable. Like, if it wasn't differentiable, then right there, you never got a negative 1/5. But guess what? That you can't assume that here because they said it was differentiable. Y'all with me? Gotta be D. I don't have time, this is a calculator problem. But this says, what if when finding the C values, guaranteed by mean value theorem of Rolle's, you got down to this equation? So basically, here's what I'm saying. I'm saying, what if you took the derivative, and you got this, right? And then you did average rate of change, and you got 8. How are you gonna solve for X? And I'm guessing most of you are gonna say, does this make sense what I'm saying right here? If you took the derivative of the function and got this, and if you did average rate of change, and you got that, my guess is you'd probably do this first. And then you go, whoa, cubed. I don't know how to factor that. What do you do to solve if you have a calculator? And I've mentioned this once before, I don't know if you were in class though. You're gonna change that to a y, graph and find what? The zeros. Literally, where is y? You just replaced it, right? Where is y? 0. Graph and find solutions. And then what else do you have to be careful about? That your solutions are in what?
The interval.
In the interval they happen to have at the beginning of the problem.
Do they have an interval in that?
No, because I was just trying to sneak this in before the wire. I don't know that many of yours are going to be graphing ones. Most of yours you'll probably be able to solve manually. But if you ever can't, man, knock it out the calculator. Just find the zeros. All right. Good day, class. Well done.